Hi everyone. This video is going to be a little bit of review about hyperbolic space. I'm going to go over some of the things we need for the next few days where we're going to talk about triangles in hyperbolic space. Even if you feel pretty comfortable with hyperbolic space, I recommend watching the whole video because I'm going to touch on a few new things that we haven't talked about before. So first I want to kind of compare locally the three main spaces that we've looked at, which are the plane. So here's a little piece of the plane, sphere. Here's a small segment of the sphere. And then locally hyperbolic space can be visualized as a saddle like this. And the key differences between these spaces can be seen by looking at what happens to lines that appear parallel as you extend them. So on the plane, if I have a line segment and I translate it to get another line segment, those two segments are going to have the same slope, and if I extend them along the rest of the plane, they're going to stay the same distance apart from each other. On the sphere, if I start with a little line segment and do a parallel translate of it, I get something that kind of locally appears parallel, but as I extend these segments, of course, they bend towards each other and eventually even hit. And same if I go along the other direction. And then on hyperbolic space, the opposite happens. So if I start with two segments that appear parallel and extend them, you can kind of see that if I extend this straight, it's going to kind of bend up, whereas this one might bend down. Same in the other direction. And so these segments get further and further apart as I go along them. So that's kind of the key local differences. And I'm going to be drawing triangles in hyperbolic space, so I want to kind of give you a way to represent those. If I draw a triangle in the plane, then of course it looks like what we think of as a normal triangle, maybe like that. On a sphere, the geodesic segments of a triangle are coming from great circles, and if I was to project that down onto a plane, which I'm always doing if I'm drawing on a whiteboard, these segments are not going to be straight lines on the plane anymore. And so this triangle, this projection of the triangle, it's going to appear like the sides kind of bend out from each other, which is exactly why the sum of the interior angles here is greater than 180. And in this case, on the hyperbolic space, if I take three geodesic segments and I project down, I'm going to get something that looks like a triangle where I've bent the edges into each other. And as we'll see from one of the group presentations, the sum of the interior angles of a triangle in hyperbolic space is always less than 180 degrees. So this kind of picture I'll use to represent a triangle in hyperbolic space, even though I'm drawing it on the plane. Okay. So the next thing I wanted to mention, one thing we can talk about is Euclid's parallel postulate, which in a plane says that there's a unique line. Given a line L and a point P, there's a unique new line that I can draw through P, which is parallel to L. And I'm not going to worry about the definition of parallel for now. But on the sphere, of course, we know this isn't true because something that locally looks parallel is going to eventually bend towards L and it'll eventually hit. So there's no such thing as parallel lines on the sphere. On hyperbolic space, however, there's many lines which go through P and do not intersect L. And this is because they all kind of bend away from each other. There's sort of a whole family of such lines. But there are special ones which kind of go as close to L as possible. And in fact, as I move, in this case, to the right, this red line is going to become asymptotic to L. So there's a unique choice of geodesic which becomes asymptotic to L as I move in a certain direction and goes through the point P. And how can we prove this? Well, we can use our map. So remember that hyperbolic space maps to the upper half plane. To note the upper half plane is H. And we know a little bit about this map. We know what it does to geodesics. Geodesics in hyperbolic space get mapped to either vertical lines in the upper half plane or semicircles which have center on the x-axis. So those are what the geodesics look like. And if I know that, I can actually prove this fact that I was saying, that there's a unique geodesic through the point P which becomes asymptotic to L. So in my picture, maybe L gets mapped to this semicircle here, and for some random point P, as you can see, there's many geodesics which go through P which do not intersect L. But there's a unique one which becomes asymptotic to L in a certain direction. And that's the one coming from the semicircle, which would be intersecting L and tangent to L at the x-axis, if we included the x-axis, although that's not part of the upper half plane. Okay, and so from this picture and knowing what the geodesics are, I can see that there's a unique line here which goes through the point P and is asymptotic to L along a given direction of L. What else do I want to say? Well, I guess I wanted to talk about triangles. So as I mentioned, I can draw kind of a representation of a triangle in hyperbolic space like this. And we've already spent some time exploring what happens, what this looks like in the upper half plane. Well, it's coming from just 3 geodesics that intersect, each 2 of them intersect at a vertex. So I get something like this. As the image of this triangle in hyperbolic space, it maps to this object in the upper half plane. Okay. And the point of this is I want to talk about ideal triangles, which we've mentioned but we haven't spent a ton of time with. So ideal triangles they're not triangles. They're made up of 3 geodesics, but none of these geodesics intersect, but they almost intersect. So each pair of geodesics is asymptotic to themselves along a certain direction. And so, for any 2 of these geodesics that I choose, they don't intersect in a vertex, but they get asymptotically close to each other as I go towards infinity. And how do I know these kinds of things exist? Well, if I go back to my map, I can draw them. So there's kind of 2 ways to do this. One, if all the geodesics are appearing as semicircles in the upper half plane, then I get something like this. Or the other alternative is if 2 of the geodesics are represented as vertical lines in the upper half plane, then this also gives me an ideal triangle. And remember that distance is distorted under this map, and the distortion is such that the higher I go in the upper half plane, the closer these points actually are in hyperbolic space. And so this distance here is shrinking as I move up. And that's why this is an ideal triangle as well. Okay. And one interesting fact is that all ideal triangles in a given hyperbolic space are congruent. Okay, so what do I mean by congruent? I mean that there's an isometry sending one, given any two ideal triangles, there's an isometry which sends one to the other. Okay, and in particular, they're all the same size. Oops. What do I mean by that? I mean they have the same area. You might look at this and say, well, this one has infinite area, whereas this one has finite area, so how can that be true? Well, I mean area in the hyperbolic sense. So, of course, this ideal triangle here, let's say it got mapped to this one. It got mapped to something with infinite area, but we're distorting distances again. And so the actual area here in hyperbolic space is finite. Even though these edges or these geodesics go out infinitely far, they get closer and closer together because they're asymptotic to each other, the two edges, and so the total area within this hyperbolic triangle is finite. And we're gonna actually calculate that area in the next video. One final fact I wanted to mention that I've kind of neglected in the class up till now is that just like with spheres, there's many different hyperbolic spaces which differ in terms of sort of how curved they are. Okay, I don't know what this is. Oops. Sorry about that. Okay, so here's a sphere, here's a sphere, here's a sphere. You know, I've got many different spheres, infinitely many, depending on what radius I choose. And locally, these spheres kind of look more and more like the plane as I increase the radius. So if I'm in a small neighborhood here, for a bug living in this little region, it looks flatter and flatter. And in the limit, I kind of can't even tell. And so I can view the plane as kind of the limit of this sequence of local patches of the sphere. And similarly, there's many hyperbolic spaces which vary in terms of sort of how curvy they are. So this one's not too bad. Local patch here looks kind of like the plane. But I could draw one which was a lot more curved, like that. And I can kind of increase or decrease how curved it is, just like I can increase or decrease how curved a sphere is. And so there's a sequence of hyperbolic spaces which vary according to a parameter. And let's call that the radius. So for lack of a better term, it's not really radius, but it kind of measures how curvy things are. So each sphere has a radius, rho, and each hyperbolic space does too. So you might be confused because I say, okay, there's many different hyperbolic planes coming from different radii, but we've only talked about one upper half plane model. So what's going on? Well, what's going on is every hyperbolic plane maps to the upper half plane. So if I have a more curvy one, it also maps to the upper half plane. And the geodesics are the same for both of these maps, but the distortion is more under this map because I have to bend things more to flatten this space out. And this one has less distortion. And so in fact, if I have a hyperbolic space of radius rho, and it maps to the upper half plane H, the distortion is given by rho over y, where this is just the height in the xy plane, or in the upper half plane. So what do I mean when I say the distortion is given by rho over y? Let me explain a little more carefully. So let me clear off my hyperbolic plane. Let's say I have 2 points in hyperbolic space P and Q, and let's give this map a name. I'll call it M for map. And let's say M maps these points to these 2 points in the upper half plane, M of P and M of Q. And suppose the distance, the Euclidean distance, the actual distance in the plane between these 2 points is given by D. And let's say they're at a height of y. So this point looks like some x1 comma y. This point looks like x2 comma y. So of course D then is just x2 minus x1, right? Now, if I want to know what is the actual distance between these 2 points in the hyperbolic sense, so let me give this a name. I'll call this the distance between P and Q. Then I can calculate it by calculating the distance on this map and taking into account this distortion factor. And so the distance in the hyperbolic sense between P and Q is going to be equal to the distance between M of P and M of Q, which is just D, times the distortion factor of rho over y. Okay? And so this tells you that as I look at points which are higher and higher on the upper half plane, the y value is shrinking. It's getting smaller. Sorry, y is getting larger, so rho over y is getting smaller. And so in the hyperbolic plane, these 2 points were closer and closer together. Okay. And similarly, as I move down towards the x-axis, 1 over y gets larger and larger. And so points which appear in the Euclidean space to be the same distance apart are actually getting further and further apart as I move down. And so that's the distortion. And so there's a map from any hyperbolic space to the upper half plane, and depending on how curvy that upper half space or the hyperbolic plane is, that determines this distortion factor, the rho in it. Okay, but all of these various hyperbolic planes are kind of related to each other by scaling. So if I scale this, if I take a little segment and zoom out really far, it's going to look like this. Just like on the sphere, if I take this and zoom out, or zoom in, I guess, it looks like that. So that's how they're all related. So the key takeaways from this lecture that I want you to have is, okay, we have these ideal triangles. We can represent them on our map of the upper half plane. And then finally also this distortion factor of rho over y. One final thing I want to point out is if I have some points, let me clear the board a little bit. If I have some points which, say P and Q, which map to points of different height, I can't just measure this distance and then multiply by rho over y to calculate the hyperbolic distance between them, because the y value is different as I move along this path. And so in that case, if I wanted to actually calculate the distance, I would have to do an integral, a line integral actually, along this line, because this y value is changing. And we're going to do something like that in the next lecture.